Oh, okay. Sorry. Yes, you didn't get one of these. So it tells you it's a first order process at 300 Kelvin. It says the reactants concentration drops from 0.95 molar to 0.45 molar in 170 seconds. What is the rate constant? So first order, what integrated rate law are you going to use for first order? The second one, right? The second one. So that's natural log of A at times T minus KT plus the natural log of A initial. So if it drops from, oh, let's write that out. Oh my God, I tried to write it out on my board. So it tells you it's first order. So we'll use this formula instead of this formula just to get you in the habit. So you're going to use the natural log of A at times T equals minus KT. And we're going to add it to the natural log of A naught. Whether you keep it inside or outside, I don't think it matters. So we're going to have 0.95 to 0.45. Which one's the initial? Huh? 0.95, 0.95. And it's going to the natural log of 0.45. And negative K. And what is T? 170 seconds, 170 seconds. So then we want to simplify. What are we going to do to simplify? Yeah, we want to isolate K. So we'll subtract this from both sides, natural log of 0.95. So we'll have the natural log of 0.45 minus the natural log of 0.95 equals negative K times 170 seconds. Now you can just go ahead and do this and put it in. Got my calculator. So here, and then how many digits am I working with? We're working with 2. So we got negative 0.7985. So it's a negative 0.80 minus natural log of 0.95. And I get minus negative 0.05. Yes, 0.051. Cool. And so that's and I get negative 0.749 equals minus K times 170 seconds. Going to divide by negative 170 seconds. Divide by negative 170 seconds. 170. And I get, what do I get? What do I get? What do you guys get? Okay, so we got 4.4 times 10 to the minus third, right? Now, what unit is here? Molarity. And what unit is here? Seconds. So our K is our K for second order rate law is our K per molar per second. Units. Is our K per molar per second? Yeah. Are we there? Cool. What do you think of that one? Yes or no? Okay, cool. Thank you for letting me know. That was cool. So, okay, let's pass out another one. I'll let you guys do this one. The tape is so your tape is paper at a time. Yeah, I think 1, 2, 3, 4. Yeah.
Is the Saturday labs this week?
No, okay, Saturday labs were rejected due to safety concerns.
What?
Yeah, right, Saturday labs were rejected due to safety concerns. Well, okay, so someone gets acid in their eye on a Saturday. Of course, I can call 911, but there's this whole accident thing which would require an administrator. The administrator is busy doing sports on Saturday.
Yeah, I think our science is good and what's on time is. Really run that.
I know, why didn't? That's true. Does everyone have one? Does everyone have one? Okay. So what are you solving for in this one? It tells you it's a first order reaction, has a rate constant, so it already is giving you K. And it says if the reaction begins at a concentration of 0.50, so that's your A naught. What will be the concentration after 60 seconds? So that's giving you your T. What are you solving for? The natural log of AT, so already in this format. So it is a plug and chug. And Jazz, you haven't seen the question yet, but I will give it to you. Pull this one over here. And that one there. What's this pen? Oh. Okay, let's switch pens. What the heck is going on? So again, a first order integrated rate law is a natural law of the concentration of A sub T. Okay, I have to use this one. Natural log of A sub T equals negative K T plus the natural log of T sub naught. It's giving us K, so negative 3.8 times 10 to the minus 2 per second. And it gives us 60 seconds. Well, look what's going to happen. The seconds are going to cancel out. And it says it begins with, and that would be the natural log of 0.5. And it's asking for this guy. So calculator works. So this is negative 63 times 60 times 3 point second function e minus 2 equals, and we got a negative, so let's cancel this. Yes.
Plus LS plus LN.
Oh, and I'm multiplying. Thank you. thank you. Oh, plus N, so. Negative 693. This is plus, and it's a plus a negative 693, so. We got, thank you. Second and second. This will be, this was molarity. This is molarity. Whoa. Mhm. Okay.
Element.
You got it.
10.9.
Do, do, do. Do, do, do. So now how do you get rid of natural log, guys? Yeah, so if you raise e to this, they cancel out. If you do it on one side, you have to raise e to whatever this is, right? So you end up getting the concentration of A T equals, if you raise e to 3.8 times 10 to minus 2 times 60, and then plus negative 0.693. Well, you can do that a couple ways. No, you can't. Can I do math? Can I add it on the other side first? Before taking E? No, I don't think I can. Right? No, because then you wouldn't be getting rid of the natural log.
That whole thing.
Yeah, E to the whole thing. So how do you get E? You do second function natural log in your calculator. So second function natural log, and then you're just putting it in, which is the 3. Oh, clear. No, not 3.8. It's, did everyone get 1.587? Oh, what?
Oh, I got one, maybe it's, isn't it negative? 3.8 times 10 to the third, so it's negative 50.
Yes. Yes. Thank you. Negative. -2. And then 60. Equals. Okay, so I have the concentration at time T to be 0.05 molar. And it started at 0.50 molar. Does that make sense that it would be less? The first order reaction, this is its rate constant. If it begins with this, what would the concentration be after 60 seconds? Got to be less, right? The conversion would be less. So everyone get that? Yeah? Super simple. You want another one? Sure. The natural log of 0.5 molar. 0.5 molar was our initial concentration. So we're putting it in there. And we're solving for the final concentration. Okay, let me get another one. Second order process. Woohoo, second order. Right? Thank you for little enthusiasm. So we're going to use a different formula for second order. Use that long arm. Oh my God, that just made me think of the Incredibles. Remember the Incredibles? They're always kind of freaking me out. The mom that could stretch. They just always kind of look weird. But I love the little baby. And the seamstress. Who was it? I don't remember. The short one, I think it's not a theme script, but.
How you doing?
Just making time. Sign up, a little bit short. Okay, so second order process. We got a positive KT. So we're gonna use 1 over AT for a second. Oh, sorry, Jess. Don't mean to keep forgetting about you. Here is the question. So we're gonna use the formula 1. Oh my God. Okay, we're gonna have to do it this way. 1 over A at times T equals KT plus 1 over A at time naught. And so how do we know to use this one? Because it says second order process. Would you? Huh? Do you like this one or do you like the one on your formula sheet better? I shouldn't force you to use the one I was taught by. You want to use the formula sheet one?
Doesn't matter.
Right, yeah, so the formula sheet one is 1 over. Yeah, I shouldn't. And then it minus 1 over K naught. Equals KT. So this is from your formula sheet, so we can just plug and chug into there. It tells you your rate constant, K, and you can see that per second order. If reactant A has an initial concentration of 0.80 molar, so our initial that's going in here, how long will it take for the concentration to drop to 0.1? So that is going here, and we're solving for T. To solve for T, just looking at this, hopefully you guys see we could divide all of this by K. And that would, when we divide this side by K and divide that side by K, we can get it all. Or we could, what else could we do instead of doing that? It's another way to solve for T, like before we plug and chug. Okay, never mind. We don't have to get creative. We can just keep it simple. So 1 over 1 minus 1 over 0.8 all over 2.6 times 10 to the minus 2. And this is per molar. Oop, this is molar, this is molar, and this is per second. And we're solving for P. Two point 6 second function E so minus 2, and I get 337 seconds. Right, so these are 1 because we just, this is that's just 1 M, so that gets rid of this, so that makes this seconds. Yes.
Sig figs will be need to write down as 340.
So sig figs here is 2, 2, and 2. Yep, 340 seconds. Thank you. The sig figs 340 seconds. Because even before it's a 7, it's a 6. Yep. So we feel good plugging and chugging rate laws. Okay, so let's take some notes on molecularity. 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 This one goes here. I gotta stick on it. And then we got more problems to do. So we are okay. Okay, so okay, we're gonna call this reaction mechanisms. Reaction mechanisms. And a mechanism is just a reaction mechanism. So all along you've been given reactants, yields, products. But a mechanism is kind of a sequence or a series of steps that those reactants go through to get to the products. Okay. So it is a sequence of bond breaking and making that occur to convert reactants. I abbreviate reactants, RXT, it's reactants, to products, PROD, reactants to products. Now, this is theoretical. This is in theory. This happens in a chemist's brain. This is for when a chemist is at one with the universe and they think it happens this way. Okay, they think it happens this way. Reaction mechanisms are what's going on right here, right? What's going on right at the top of that energy diagram. And as I said, no one really knows. So chemists will guess. They'll kind of guess and they'll come up with a potential sequence for which bonds are going to break and which one. Oh, it's just the energy diagram over process, reactants, products. Remember this guy? So it's at that transition state that we're talking about. So, but this is only happening in a scientist's brain, in a chemist's brain, which, because it's all happening in we're just kind of imagining this, we make it easy for ourselves. You dropped your lead, it's under your chair, don't lose it. That stuff's expensive. There you go, $7.99. You're welcome. Yeah, you're looking at it. You're looking at a lead superhero right here. Okay. Well, you'll see what happens with reaction mechanisms. So then a traditional reaction will be broken up into the steps. So the steps that are imagined are called elementary reactions. Are called elementary reactions. Now, again, these are imagined because the reaction mechanism is what actually is going on. So we come up with elementary reactions. What's cool about an elementary reaction is, I guess it's defined as a singular molecular event. So it is a singular forming a bond or a singular breaking a bond. So if you have a whole bunch of reactants and they all need to be broken up and then they all need to be put back together, an elementary reaction is just one at a time. You got to look at it one at a time, one element breaking, one element being put back together. So a reaction could have multiple elementary reactions in the entire reaction mechanism. Reaction mechanism is made up of elementary reactions. The elementary reactions are a single event that occurs. So it's a single breaking or a single forming. We don't put them all together because that's what our equation does for us. That's what we've always looked at, is it all put together. So a mechanism is a way to break it apart. Now, molecularity is just the number of events in an elementary reaction, not the number of events, the number of reactants in an elementary reaction. Molecularity is the number of reactants in an elementary reaction. So we got elementary reactions, we got a reaction mechanisms, and we have molecularity. So molecularity, there are 3 vocabulary words that you need to know under molecularity. Something can be unimolecular. If you are unimolecular, basically you have one reactant. And an example of a unimolecular elementary reaction would be ozone breaking down into O2 and oxygen. We only have one of these. There's only one reactant, so we would call this unimolecular. Now, all of this is really based on collision theory, right? So collision theory, when I say it's in the chemist's mind, but they are being guided 100% by collision theory. So it is still how many things need to hit each other with enough energy and in the proper orientation. So that goes back to this. So it's still being ruled by collision theory. So then you have, after uni, you have bi. What do you think bi is? Yeah, so bimolecular. So we have 2 reactants. Now, when you have 2 reactants, I'll keep with the O3, like O3 plus O, and that's going to make 2 O2s. So now we have an ozone molecule and then an elemental oxygen, an ozone molecule and an elemental oxygen. Those are 2 different reactants that have to hit and combine. So they're also hitting themselves, right? They're hitting themselves and they have to hit and combine in the right orientation with each other. Does that make sense? Okay. And then molecular is 3 reactants. So a react, this is super rare because if we have A, B, and C, and they have to make D, right? That means A has to have enough energy and hit in the right orientation. So here's A. And B has to have enough energy and hit in the right orientation. And C has to have enough energy and hit in the right orientation. So this is like a 3-car accident, right? You don't hear about many 3-car accidents. 3 cars just hitting each other at the right. You hear about 2-car accidents and 1 car's run into trees and all kinds of other stuff. Or like a 6-car accident. Think of 6 cars would all have to be going to the exact same point at the exact same time and all not seeing each other, right? So molecular, incredibly rare, tetramolecular and above, super duper rare, if not just theoretical in general. So this is literally letting you know how likely the reaction is to occur, the elementary reaction is to occur. So that's molecularity. Just a kind of a fancy word. So I don't believe, I think you need to know the vocabulary. There's 3 or more reactants, but I don't think there's going to be a single problem that you would ever have to do other than definition wise, to know the definition of a reaction mechanism. So do we want to take a look at one? Yeah, Jazz, are you done copying that down?
Yes.
That startled me a bit. Okay. Totally startled me a bit. So let's do an example. Okay, so this one is going to be bimolecular. I'm going to do a bimolecular elementary reaction, and basically 2 nitrogen dioxides will yield nitrogen trioxide and nitrogen monoxide. So everything is, and this is kind of the first step or the first elementary reaction. And then the second elementary reaction will be NO3 plus carbon monoxide yields NO2 plus carbon dioxide, right? And now step 1, so this is a reaction mechanism. Reaction mechanism. They won't tell you it's bimolecular, but both of these are bimolecular. So 2 NO2s is like NO2 plus NO2. So there are 2 reactants that can hit each other. And this is 2 reactants that can hit each other. This isn't the reaction that you would see on a worksheet. This is the reaction mechanism. So first problems they can ask you is they can literally say, what's the reaction? They can give you these and ask you for the reaction. So what you can do is, if it, just like in math, if it's the same thing on both sides of the arrow, you can get rid of it. So I see I have an NO3 here and an NO3 here, NO3 and an NO3. So they go away. Also, I have an NO2 and 2 NO2s here. So I can get rid of this and I can get rid of one of those. Does that make sense? So you simplify where you can. Now, so I guess step 1, you want to simplify. And add together the elementary reactions. So now notice we have a reactant yielding products. We think this happens. We think the NO2 breaks down in this. We have NO3 as a product here. And then we have NO3 as a reactant here, but we're never going to see it in the actual chemical equation. When we add this up, we're going to have NO2 plus CO, and that's going to give us what's on this side, okay? Nitrogen monoxide and CO2. So we never see NO3. So this is known as an intermediate. An intermediate shows up as a product in one of the elementary steps and a reactant in another elementary step, but it is not in the final equation. That would be an intermediate. An intermediate. So they could ask you for the formula. Now, let's say this is a slow step and this is a fast step. You can also get rate laws from this. So if you were to write the rate law, remember rate laws only come from reactants, right? If you were to write the rate law for the first elementary reaction, what you gonna write? Rate equals K times NO2. Now, remember this NO2 was raised to the 2, like originally, right? If we go back to the original one, elementary reactions, the order is, get this, the order is the molar coefficient. In elementary reactions, the order is the molar coefficient. So the rate law for the slow is that, because you can just use the molar coefficient. Because this is happening in our head anyway, so why not make that the rate order? So then can you do the rate expression for the fast elementary step? That's going to be rate equals K. Remember, it's little k. And we've got NO3. That's to the first. And CO also to the first. That makes sense to you guys. Yeah. Now, the only problem is this is an intermediate. This is an intermediate. So you can't have that in a rate expression. You can't have an intermediate in a rate expression because it is not part of the rate law. But remember, you're only as fast as your slowest. You're only as fast as your slowest. So looking at this, if you were asked for the rate law for the whole deal, it's just this guy, right? Because you can't get any faster than your slow step. Yes.
Could you talk a little bit? How do we know that one is slower than the other?
I just picked it to demonstrate that you can't have an intermediate and your rate is only as fast as one of these.
Will they tell us?
Yes, absolutely. Yes. Yes. You do not have to be one with the universe. You do. I mean, you can if you want to be. I'm not saying you don't. I'm not saying you aren't. I'm saying you don't have to be. We'll be given that information. You want to do another one? Want to do another one? So let me try to ask you questions. So the rate determining step is always the slow one, right? The rate determining step is always the slow one. Notice here, the slow step is occurring first. So let's think about this. This takes a while, but this is converted to this. It just takes a while, right? But once you have these two, no problem with this one, nice and fast. Are you there? So it's not going to go any faster than this, because this is like waiting. It's chopping at the bit. It's waiting for that NO3. And as soon as it gets it, it goes. So the next one I'm going to show you is when the fast is first. When a fast reaction, elementary reaction is first. So let's look at nitrogen monoxide and nitrogen monoxide, two reactants, and they make N2O2, boom. And this is the fast reaction. And then we have N2O2 as a reactant. It's a product here. It says as a reactant down here. We're going to add that to oxygen, and we're going to get 2NO2. This is the slow reaction. One is fast and one is slow. So let's first just think about this. After you guys write it down, we're going to think. If it's going really fast, so that means N2O2 is being made really fast, and it's being held up by the second step, right? So it's almost like piling up. It's piling up on this side. So this is very similar to adding cheese into that side of the bowl. What's going to happen is this fast step will start going the other direction. Now, next unit is all about equilibrium, but you guys should know or remember some of it from Le Chatelier's principle, that these guys can go both ways. And you put a stress on one end, the reaction is going to accommodate that stress by shifting. So instead of this nice flowing downhill, since there's something blocking it, the concentration of N2O will actually shift the reaction towards the products. So this is a fast step first is going to be in equilibrium. Well, if the fast step is in equilibrium, and you probably don't remember, but the rate of the forward reaction is equal to the rate of the reverse reaction. So if you had to write the rate constant or the rate law or rate expression, that means the rate of the concentration of NO raised to the 1 times NO raised to the 1 or NO raised to the 2 bimolecular second order is equal to the rate of N2O2 formation, right? So both of those are equal. Does that make sense to you? Okay. So yeah, you could be asked to, so yeah, what did I just say? I just said that the rate equals K times NO there. You could write it like that because there's two of them. You could put that together. This is just another way to write it for bimolecular, meaning you could also say it's equal to K NO the 1 NO to the 1. So I know my order just from my molar coefficients. Well, that is also equal to K N2O2 to the first, right? These are equal to each other. Does that make sense? Because it's at equilibrium. And then looking at this, if we wanted to write the actual equation, we are going to cancel out whatever's on both sides. Is there an intermediate in this reaction? Yes. What's the intermediate? Yeah, N2O2 is the intermediate. And then is there anything else? No. So when I add this up, I have 2 NOs plus O2 yield 2 NO2. So this is me adding up. So this would be the actual equation. Now, if you had to do the rate law, right? If you had to do the rate law for this, let's look at this. I can say rate equals, so that's all for the fast. If I go, the slow is still the rate determining step, but if I write the rate equals K times N2O2 to the first times oxygen to the first, I can't have this because that is an intermediate, and I can't have an intermediate in a rate law. Anyone know where this is going?
Like the
Yeah, if these two are equal, if these two are equal, I can plug this expression in for this expression. And that means I can get rid of this expression. So the rate will equal K and O second, O first. Now, all the K's kind of go together if you're wondering about the different K's. So all the K's you just lump together, even though you're dividing a K and one is an inverse K, it's still just a constant that you're going to multiply the rate law by. Pretty cool. I think it's pretty cool. So those are some, let's do some reaction mechanism questions. Okay. Okay, Jazz, I remember you. Here we go. Remember this one. This is it. This is what? Very welcome. Tired? Yeah, been ready to go. So I'm waiting. Everything is sprawl out. Thank you. Boom. Boom. And boom. Okay, so we're given a mechanism below. Ooh, forgot about this. That's kind of cool. So one cool thing about these mechanisms is here we have an intermediate. Can everyone find the intermediate? It's a product in one and a reactant in the other that does not show up in the overall. Yeah, IO, the ion IO is the intermediate. But we also have a catalyst. A catalyst starts on the reactant side. Oh, are you missing one? The catalyst is not used up in a reaction, right? But it's definitely on the reactant side. And it comes out exactly how it was. So here, except for that I didn't superscript the negative charge, it has a catalyst. It has the iodide ion as a catalyst in this reaction. And I don't know when we're supposed to cover catalyst. So there are three. Obviously, you know of biological catalysts, the enzymes. In chemistry, we can use acids and bases that hold proton as a catalyst also. Have you heard of a catalytic converter? It is, well, your cars have a catalytic converter. They get stolen all the time. They're made of palladium, and what they do is they catalyze the breakdown of toxic gas coming out of your engine into less toxic gas coming out of your engine. So all cars are required to have a catalytic converter. And basically, so when you're dumping out a whole bunch of hydrocarbon waste, it's before the muffler, and it just tries to convert that as fast as possible to carbon monoxide, another bad gas, but just still not as bad as without a catalytic converter. So it doesn't look like smoke's coming out of your car, but it still is, you just can't see it. But they're very important, and they get stolen all the time because they're very expensive. It's like $1,000 a pop. And it's one of the things that you totally need to recycle. So they're taken out of cars all the time. So you got to recycle your catalytic converter. Okay, that was slightly off topic. Okay. So we want to write the overall equation for the reaction. So to do that, we're adding them together, but first we get rid of anything that we see on both sides, so we can get rid of our iodate when they're there. Get rid of this. An intermediate. It's an intermediate because it starts as a product. We can get rid of our catalyst, right? That's a reactant. That's a catalyst. And then I don't see anything else. So when I add it up, I have 2H2O2. So 2 peroxides yielding 2 waters and O2. Now, I was taught that you put your catalyst on top of the arrow, but I haven't seen that yet. But if you see something on top of the arrow, that shows you that you know what your catalyst is. Does that make sense? It's a catalyzed reaction. Identify the overall, identify the reaction mechanism, identify the catalyst, identify the reaction mechanism. This is the reaction mechanism. I probably meant to write something else. Oh, probably the intermediate, the reaction mechanism's intermediate. So we just did that. And then identify the catalyst and determine the rate law for this reaction. Determine the rate law for this reaction. So what is the rate law for the reaction going to be? Can I use the slow reaction? Right, but you're not going to include a catalyst in a rate law. Okay, you're not going to include a catalyst in the rate law. So your rate is going to equal K H2O2. What order is this? Right, we already know it's second order. See how easy orders are with reaction mechanism? Super cool.
Yeah.
Yeah. Will you be able to do these problems? You want a quick quiz? No. You guys take all the joy. Killjoy. Oh, killjoys. Okay, I got one more. I think I have one more. And one more problem. I don't need to have, oh, one more problem. Holy crap. No, I have tons of problems. Let me find an interesting one. Okay, here we go. Write the overall equation for the reaction and determine the rate law of this reaction. Ooh. Don't forget, fast means that. I'm not going to pass it out. I'm not going to pass it out. You know, you get kind of fast at writing down these equations. Is there an intermediate? Holy crap. Why is this here? Is that what it is? Thank you. I don't know why I made it so. Why did I make it small? Yeah, you're right. It's the overall order for this reaction. Overall order for the reaction.
Three.
Okay, so you don't say three, you have to say third. You have to say the cardinal.
Third.
Third, right? So if you put three, it'll be marked wrong on the AP exam. Don't look at me like I'm being a jack here. I'm just telling you what they'll mark wrong. And first, second, and third order, zero order, you use first, second, third, zero. You don't use 1, 2, 3. Right. So everyone got this? Everyone add it together, right? And everyone get the rate, right? And then remember, you add M and N to get the total order. This is second order with respect to nitrogen monoxide and first order with respect, but
Instead of CO.
yeah. Yes. Thank you. So it's first order with respect to chlorine, second order with respect to nitrogen monoxide, and third order overall. Now, what molecularity does the first reaction mechanism step have? It is bimolecular. Bimolecular. And what molecularity does the second reaction? Yep. Bimolecular. Makes sense. Super cool. Let's do another one. Here we go. We got two things going on here. And a big old typo I see just now. Write the overall equation for this reaction. Which of the two elementary steps in this process would you expect to occur at a faster rate? Explain your answer. What?
Wouldn't it be A plus B plus C goes to A, B, C?
A plus B plus C. Okay, so so you are crossing out that and that, that and that. Yes. What's the intermediate? AB, what's the catalyst? B. Well. Okay, we'll go with that. Now, which one's gonna happen at a faster rate? One says the second, one says the first. Okay, first step, what would you say to explain your answer?
Bimolecular, and those happen a lot more often than molecular reactions.
Trimolecular. Trimolecular is the wrong word. Permolecular. Yep. Okay, so very good. Excellent. Yes. Yes, I think that would be perfect. Would you have to define? No, because you are defined. So if you wrote down everything you said, that would be right. If you stop after the first sentence, it would be wrong. Right? Now, why did you think the second step was occurring at a faster rate?
It's like a catalyst.
So the catalyst would be on the reactant side, so it's in the first step also. Right? It's just not used up in the reaction. So the catalyst is also in the first step. So, but yeah, if you, yep, I get you. I get you. Makes sense why that is faster? Okay. Let's do another one. Yes, please. I love it. It's so much fun. I'm so ready. Okay. Consider the slow steps from the two different chemical reactions below. Okay. So they're both slow. Which of the two processes will have the faster rate? Explain your answer. So we know there's slow steps because they're not, neither one of them's in equilibrium. They're not actually, these are two different chemical reactions, and you can see that, you know, P and Q has nothing to do. So these are just pulled from two separate mechanisms. Which of these processes will have the faster rate? Explain your answer. So rate equals K times the concentration of P times the concentration of Q, and rate equals K times the concentration of Y times the concentration of Z, both bimolecular, both second order. Yes.
Could be the second one because the K value started.
Yeah, it's that easy. What's going to happen if you put 5 in for here and 7 in for here? A bigger number is going to make the rate larger, right? Because you're just multiplying it. Does that make sense? So a bigger number, that's exactly, you want to use the rate constant. And when you explain your answer, the larger the rate constant multiplied by any concentration is going to give you a larger rate. Just based on its relationship in the chemical formula, not in the chemical formula, in the mathematical expression. Would you guys have gotten that one right? What does it mean when you just stare? No idea. You should play poker for a living. No idea. Okay, you want to do one more? Yes, please. This is so much fun. I've never had this much fun. This is the best class ever. Which one is it? Okay. The one we haven't done. Have we done this one? Yes, no. Have we done this one? No. Have we done this one? Give me the rate law. What'd you get? What'd you get?
Equals N2O to the second order. N2 first order and O2 first order.
Rate equals K
N2O.
N2O squared. That's it. You guys good with that?
How about N2 and O2?
N2 and O2. So rate laws are only based on the reactants, because remember, we are only interested in that instantaneous, that very beginning of the reaction rate, right? Since we don't really care about further up when we do our rate laws. So we want it right at the beginning, wherever that beginning is. Could also be here. So we're only looking at our reactants. We only want to look at our reactants for rate laws. Simple? Okay. So next class. We are, you are nice. Going to calculate. Okay, so basically you're going to put a piece of marble or CaCO3 into 6 molar HCl and 7 CaCO3 and in 3 molar HCl. Yesterday we did it, Friday, Richard and I did it in 12 molar HCl. And basically we're using the acid here as a way to quickly break down calcium carbonate into carbon dioxide, right? So it's the decomposition of CaCO3 into CO2. And this obviously is gas. So you see bubbles and the gas is, coming up. This is CO2. And the hydrogen ions and chlorine ions are aiding in this process. And basically the rate at which this is appearing, the CO2 is appearing, would be equal to the rate at which this is disappearing. Well, when we deal with rate, we deal with concentration, right? So this is our initial molarity. This is our initial molarity. So that would be let's say this is A. So this would be A naught. A naught initial molarity is 6 molar. So we can have it here, 6 molar. And it will disappear. And we're going to run it for 20 minutes. So we got a time rate, and it's going to be measured every minute. So our delta T is 1 minute. And we're trying to get molarity per minute. And what has molarity per time? Rate is in molarity per time. So, and ultimately after 20 minutes, so total time will be 20 minutes. I know, sounds like fun, right? What is the new molarity? So that would be A at time t, where t is 20 minutes. What is the numelarity is what you're going to be solving for. And you'll be collecting a bunch of data because this will be sitting on a balance, right? So maybe it starts at 50 grams, but what happens when carbon dioxide bubbles away? The mass is going to go down, right? So that mass going down is the CO2 appearing. That mass going down is related to the HCl disappearing, right? Because it's whatever rate this is going away is the rate that this is being used up or going down, disappearing. So the concentration of the acid will be going down based on the time. You'll be able to graph these and figure out if this is a first, second, or third order. This is not an elementary reaction, right? So there's a lot of stuff going on in here. So that's the lab you're going to do, but you're going to set it up and you're going to film it. And you're going to collect the data later by going through on your phone. You know how the time comes up when you fast forward and stuff. So the time is going to come up and you'll have to write down that time in a spreadsheet and you'll look at the mass on the balance and write that down. And then you go to the next minute and you'll write down what the balance says and what the time says. So every lab group needs a working phone charged enough to record a 20-minute videos, because you're doing it for 6 molar and for 3 molar. Damn. Right? You don't want to sit there and record and write it down every minute, do you? No. So you're going to set it up, you're going to leave it, you're going to come back here, and we are going to cover, since we got through reaction mechanisms and you got through rate laws, what's I think reaction mechanisms, then it's the lab. We'll go over some of the lab math because that's pretty funny, complicated. How'd you get your phone? Rubber arms? Uh-huh. Do we have homework for next class? Oh, yeah, work on the problems in the packet. Work on the problems in the packet. You now know how to do some, especially towards the back of the packet. I might have gone out of order. I'm pretty sure that Raimondo's collecting and grading the packet. So that means I would have to collect and grade the packet.
I didn't hear why this.
Because K is larger.
No. The one like the.
Oh, because it's a lot rarer for 3 cars to run into each other in an accident than 2 cars. Right? The molecularity for here is bimolecular and this is trimolecular, much rarer of an event.
I'm not gonna be here next class, but I'm like this.
How many people have a history field trip? You have a history field trip too?
No, I'm just. No, she does.
She does? You do have a history field trip too. Do you have a history field trip too?
It depends if we have history on plot or even.
Do you have a history field trip too? Oh, okay, good thing it's being recorded.
Yeah, and can you record like when you're doing the calculations like on your screen? like you were talking about how you're gonna do the math for it,
Yeah.
like during class, can you like record your screen?
Jeez. My calculations just confuse you guys.
But like, if we're having a.
They help a little. They help a little.
No, like, if we're having like the lab practical, like, no, it would be
Okay.
helpful to like.
Okay. Yeah, yep.
Okay, thank you.
Jazz, are you still there? I think she hung up. Do you know,
Yes. No, I'm
Oh.
still here.
you have the field trip on Thursday also?
No, mine is tomorrow.
Yours is tomorrow. You're gonna make it?
Yes.
Okay, cool. Hopefully this helped you. And
It did.
Yeah.
Thank you.
so I'll see you Thursday. That's good to know, but apparently a bunch of people won't be here, so definitely bring your phone ready to go. Sound
Okay.
good?
Yeah. Thank you so much.
Not a problem. I'm in the meeting.
Bye.
Yeah.